today I'm going to talk about how every millisecond counts for virtual reality and how to render faster for the new medium. So my name's Dominic Eskofier. I'm kind of like a VR nerd. I've been around since about 4 years, ever since I tried the original duct-taped prototype of the Oculus Rift when Palmer showed it to me at Gamescom 2012. And ever since then, I became a huge believer in virtual reality. I founded the Oculus subreddit. My handle there is uDoodlesack, so in case one of you is browsing Reddit on a daily basis, please be sure to contact me there. I'm also a meetup organizer in Munich, so if you're ever in Munich and want to see some cool virtual reality stuff, hit me up. I'm on meetup.com and all those different places. I've also founded my own virtual reality company and brought it through an accelerator program in Silicon Valley. But now I'm actually responsible for the European VR business at NVIDIA. And so I'm there to help developers get the most out of their hardware, get the most out of their software, to support them with hardware, to support them with access to our SDKs, maybe even exposure in terms of events when we can show something cool. So if any of you has some cool demos, please make sure to get back to me. So I said that I'm a huge believer in virtual reality, and I believe that it's going to transform a lot of industries, and not only the entertainment industries, where things like gaming, live sports events, movies, concerts, all these things will be changed by virtual reality in the short term, but there's also a lot of industry segments that can be transformed by VR as well. There's a ton of medical applications. So, for example, only a couple of months ago, a baby had a surgery where it was a super complicated surgery, and the surgeon wasn't sure if he could actually manage to do that. And he saw a scan of the child's brain in virtual reality, and thus was able to conduct the surgery in a much better way. And these are only just a couple of things where VR can really shine. There's design. So right now, Markus Kühne, a good friend of mine, is talking about the Audi VR experience in the other room. But I'm not going to talk about this because you guys are all here. So I'm going to dive right into how we want to fuel the ecosystem for building amazing VR content. And the headsets obviously are one part of that, but there's a huge ecosystem around that. There's things like input and tracking, how do you interact with the game world. There's things like capture and streaming, so how do you take movies for virtual reality, how do you bring that to the headset. All these things combined with game engines, app developers, platforms, and stores, we want to tackle all of these different things at NVIDIA. And there's a lot of computing challenges in virtual reality, as you probably are all aware. There's not only the graphics, but also the audio part, the touch, like interaction, haptics, and also the physical simulation has to be on point to give you a really good immersive experience. So there's a lot of challenges from that angle. One of those pillars for the challenge in VR is the ultra high resolution that you have and the frame rate. So you have to drive the display at 90 FPS because otherwise the image will get jittery, and that will lead to a very uncomfortable user experience. And also you have a larger rendering target. So you're targeting 2 displays at a higher resolution, and essentially what that means is that VR needs almost 8 times the computing power to render in a 3D world for VR. And the second pillar of that is latency. So latency is kind of like the nemesis for people in virtual reality. You don't want your image as you move your head to lag behind that input that you get. And the usual pipelines are not optimized. The usual game rendering pipelines are not optimized for latency because it's just something that you don't really need in a usual game engine. There's a couple of steps that introduce latency on the way. So the headset position is being sent to the CPU. That gets processed. That gets submitted to the GPU. The GPU does the rendering and sends it to the scan out of the display. And within each of these steps, there's latency involved. And we're tackling all of these individual steps. But before I go into I got one question. How many of you are actual developers in this room? So how many of you are working with game engines? Okay, that's good. How many of you are from a non-technical side? So would like to get a little bit of an intro? Okay, cool. I'm still going. Yeah, it's obviously a bit harder to raise their hands when that question is involved. I still want to go a little bit into detail about how rendering works in a 3D space because we have something that's called simultaneous multi-projection in our latest GPU series, And to get into that, I want to reiterate what 3D engines actually do when they're rendering an image. So at first, the GPU creates the 3D geometry, and that 3D geometry later on is projected onto a 2D surface that essentially is similar to the 2D view to your monitor that you see. And that 2D screen then gets colored and shaded with the pixel values of the scene. For VR, it's a little bit different. So most of you are probably aware that VR rendering is different in the terms that you're looking through two lenses. The lenses warp the image. The game engine puts a distortion shader over that to actually make it look to the user as if you were looking onto a rectangular image. And what you see here is that you're actually losing a lot of image information on that way. So for example, if you take a look at the red square, this is getting squeezed down. So essentially, you don't really need to render those parts of the image at full resolution. And that is something that we've introduced in our Maxwell generation, so the 9 series of NVIDIA graphics cards. And that's one thing called multi-res shading. So essentially what you do is you split up your image into 9 different viewports. And then you render the main viewport at full resolution, and you render the outer parts at lower resolution, because they get stretched anyway to your peripheral vision in VR, so it's not really a loss in terms of quality. And then what we're doing now with the Pascal series, so with the GTX 10 series of graphics cards, is we actually render to a lens-corrected surface, which means that the process that is introduced with multi-res shading is actually enhanced a little bit further. And what that leads to is an image that is actually gets rid of all the pixels that you don't really need to render. So that means that it actually puts less pressure on the pixel shader. So the pixel shader part of things is already optimized. What you can now do to get the same kind of performance gain for geometry is something called single pass stereo rendering. And that what that usually means is in a normal rendering pipeline for VR, you're rendering 2 images, one for the left eye, one for the right eye. This is nothing new to you, of course. But what you have to do usually is render 2 geometry passes. And something that we've introduced with the Pascal series is called simultaneous multi-projection. And that essentially means that you do only 1 geometry pass instead of 2, and get the same image quality out of that rendering phase. So what that essentially means is you can have twice as much geometry in a scene at the same performance level, which is a huge gain for virtual reality. And then I've already talked a little bit about the motion to photon latency, how from the head movement to the final image to the photons hitting your retina, that should always be under 20 milliseconds. And there's a couple of tricks involved that most of you probably know. One of them is called TIMEWARP. So in a usual rendering pipeline, what the engine does is it samples the head pose of the user, sends that to the CPU. CPU processes that, submits it to the GPU. The GPU flips the display. So line by line, the display gets scanned out, and then the backlight flashes, and that's the image that the user sees. What TIMEWARP does is it does the same thing, so it sends the image information to the CPU. The CPU is submitting that to the GPU. It's rendering the full scene, but then at the very last moment, the GPU actually samples the information that's coming from the head tracker, and then uses that information in the change of head position to shift the image just a tiny little bit. And that leads to you seeing an image that's closer to what you would expect, thus reducing perceived latency in virtual reality. And the cool thing is, with the new Pascal graphic series, we're actually making that already reduced latency even smaller by using something that is called preemption. So what preemption does is usually when you're rendering, you have to take a relatively conservative approach to the amount of time you need for the preemption request. So usually in Maxwell, for example, in older graphics cards, you had to wait for the last draw call to finish of the GPU. With Pascal, you have the ability to actually have a finer granularity when it comes to interrupting the GPU and injecting that time warp at the very, very last second. So again, even within the time frame of 11 milliseconds that you see on the bottom here, you still can squeeze a couple of milliseconds out because, as you know, every millisecond counts for VR. So this is what we're doing on the graphics side of things. We're using faster pixel shading with lens matched shading to actually reduce the load on the pixel shader. And then on the other side, you can have twice as much geometry detail in a scene by using things like simultaneous multi-projection and multi-res shading. And we've also talked about how to reduce latency by using a faster time warp with preemption. And all of these things are combined in our VRWORKS SDK. So VRWORKS SDK is for developers so that they have the ability to use all these hardware features to drive as much performance in their VR apps as they can. But graphics is not everything. So to have a really immersive experience, you also need very proper audio. And simulating audio in VR is a little bit tricky when compared to a usual desktop setup that you're playing on, or even a 5.1 setup. Usually you have a stereo setup or a 5.1 setup. That's kind of easy from an algorithm point of view. But if you really want to do something mind-blowing in VR, you have to go for directional audio. So as you turn your head, the sound always has to come from the right direction. That's very, very important. Because there's a couple of cues that the brain uses to actually measure where a sound is coming from, how far away it is, and so on and so forth. And also things like propagation. So for example, as I'm talking, my voice gets reverbed off of the walls of this room. This is something that's called propagation of sound. And that is also very, very important to take into account when doing audio simulation for VR. And I've already touched this a little bit. Directional audio is the keyword here. So what your ears are usually doing is they take into account the amount of time that a sound needs to come from the source to your left ear and then to your right ear. And as the distance is different from the ears, your brain is actually used and trained to realize that small time difference in the sound waves reaching your ear, and from that you can tell where it's coming from. Things like the level of sound are also super important, but also crazy things like spectral cues. Essentially, your voice is getting reflected off of your shoulders, off of your neck, off the back of your ears even. And all these kind of things are important to get you the feeling of, okay, this sound actually sounds like it would in real life, which is something that you obviously want for virtual reality. So the VRWORKS audio is taking care of all of that. It models the direction and propagation using ray tracing. So it uses our optics engine that is running on the GPU. It's GPU accelerated to actually see how sound propagates through a space. And it does that with a mathematical method called ray tracing. And it essentially shoots out a ray from the sound source, sees the reflections, and sees when and where the sound is hitting the user's ear. Sorry. And what this essentially does is, what the SDK does in the background is it takes the sound source, so the input from the game engine, it determines location and orientation of the sound source, then it takes into account the environmental geometry and also the environmental material, which means that as you talk, for example, the sound of my voice is getting reflected differently from the wooden back here or from the carpet on the floor. So we're essentially using a method similar to physically based rendering, where we take into account what kind of materials are there. And then we run it through our optics engine in ray tracing, and the output then takes into account things like occlusion of sound, absorption and reflections. It uses a head-related transfer function to get down to those details like the back of your ears and the other spectral cues that I talked about, and then things like reverb, for example. So a church hall should sound way different from, for example, just a small room. That is very important for a very immersive experience. And then another thing is VR touch. So you wanna be able to interact with the game world in a very, very convincing way. And we're doing that through our physics layer. And I don't want to get into too much details because this is a topic that people could be talking about forever. What I really want to show you is that we have a set of things that you can use on top of the performance enhancements. So there's a whole physics SDK that you can tap into, which allows you to render destruction of objects, that allows you to render water, for example, in a way that water should flow. It allows you to render hair, and all of these things are very useful. Well, we've seen that already. When you package them all together. So what I would like to ask you is check out our NVIDIA VR Funhouse. It's a very fun demo that actually was used just as a tech demo in our dev lab. And people were just using a sandbox to play around with the stuff they were doing in virtual reality, get physics interaction in there, get cool looking stuff in there. And then they realized, hey, this is actually fun. We could make this a game.